Okay, I hope I'm audible to all the students who are attending this lecture. We continue with point estimation in statistics. Okay, and in the last lecture of point estimation, we were discussing about what is meant by a point estimate. We had also talked about what is meant by a point estimator. We had also talked about sample mean being a point estimator of population mean. Okay, and we had also talked about two desirable properties of point estimators in the last lecture. One was linear estimator. So all students can refer to the definition of a linear estimator. Okay, and then we had also talked about unbiased estimator in the last lecture of point estimation. Then we were doing some practice questions based on the unbiased property. Let's continue with the same practice questions. So practice questions based on the unbiased property of point estimators. We talk about practice questions based on the unbiased property of point estimators. Okay, so we had done a few questions in the last lecture. In fact, I had given one question for homework to all the students. I hope students have taken that question seriously and have solved it. So let's look at another question. So let capital X1, capital X2, dot 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 capital Xn be a random sample from a distribution with mean mu and variance sigma square. Then show that the question asks us to show that the estimator sigma hat square, which is also called the sample variance S square summation xi minus x bar square upon n minus 1, is an unbiased estimator of the population variance sigma square. The question also asks us also show that the unadjusted S square, which is summation xi minus x bar ka square by n, is a biased estimator of sigma square, and also find the bias of S square, the bias of unadjusted S square. So this is our question. Okay, let's again visit the question. The question is simply asking us that x1 to xn is a random sample from a distribution with mean mu and variance sigma square. We need to show that the sigma hat square, which is S square, the sample variance, which is summation xi minus x bar square upon n minus 1, we need to show that this is an unbiased estimator of the population variance sigma square. And at the same time, we also need to show that the unadjusted S square, which is given by this formula, is a biased estimator of the population variance sigma square. At the same time, the question also asks us to find the bias of unadjusted S square. Okay, so let's prove this. So we need to show that expected value of S square is equal to sigma square. So let's start with the proof. So consider S square as 1 upon n minus 1 times summation xi minus x bar ka square. So therefore S square is 1 upon n minus 1 times summation xi minus x bar. I can write summation as guys, this is I going from 1 to n. So summation as I goes on from 1 to n, a square plus b square minus 2ab. We have adopt this identity, then we get therefore s square is 1 upon n minus 1 times. I can open up the summation, so I can write summation as I goes on from 1 to n xi square. Okay, plus x bar ka square if I add n times. X bar square if I add n times, I get nx bar square minus 2x bar into summation as I goes on from 1 to n xi. This is what I get when I open up the brackets. Okay, so then I can further separate it and write it like this. S square is 1 upon n minus 1 times summation as I goes on from 1 to n xi square. Okay, plus nx bar ka square upon n minus 1 minus 2x bar into, now guys, summation as I goes on from 1 to n xi is nothing but nx bar only. All of us know that x bar is what? Summation xi by n. Therefore summation xi is nothing but nx bar. So this I can write 2x bar into nx bar divided by n minus 1. I hope all students have understood this step. We have taken the denominator in every term and we have written it like this. So s square becomes 1 upon n minus 1 times summation as I goes on from 1 to n xi square plus nx bar square upon n minus 1 minus 2 nx bar square upon n minus 1. Okay, so let's continue with the initial portion. So I'm erasing this off, the initial part. Ultimately, we need to show that expected value of s square is equal to sigma square. Now our s square has come out as this. This is our s square. So I can further write it like this. Therefore, my s square is 1 upon n minus 1 times summation as I goes on from 1 to n xi square. And this term minus this term will make it minus nx bar square upon n minus 1. Now I can take expected value of s square as 1 upon n minus 1 times summation as I goes on from 1 to an expected value of xi square minus n upon n minus 1 times expected value of x bar ka square. Now guys, you should remember that x bar itself is a random variable. Since x bar itself is a random variable, I cannot take it outside the expectation. It's expected value of x bar square because x bar itself is a random variable. So I hope students have understood. We have taken expectation on both sides. So expected value of s square is 1 upon n minus 1 times summation as I goes on from 1 to an expected value of xi square minus n upon n minus 1 times expected value of x bar square. Okay, now let's make some valid substitution. So I'm erasing everything on the right hand side. Let's erase all this. Let's make the valid substitutions now. So this becomes, so I can write it like this. Now, all of us know that variance of xi formula is expected value of xi ka square minus expected value of xi whole square. This is the formula. So variance of xi is sigma square. Expected value of xi ka square we need to find out minus expected value of xi is mu. So mu square. So this implies expected value of xi square is sigma square plus mu square. This is one substitution we make. And we also know what is variance of x bar. So variance of x bar is expected value of x bar square minus expected value of x bar ka square. Now variance of x bar is sigma square by n. All of us know variance of mean is sigma square by n is equal to expected value of x bar square we need to find out minus expected value of x bar is mu ka square. So this implies expected value of x bar square is sigma square by n plus mu square. This is another substitution we make. That means in this term, instead of this term, I can write this term, and instead of this term, I can apply this formula. So let's erase this on the left hand side. So I can write it like this, that expected value of s square is 1 upon n minus 1 into, now expected value of xi square is sigma square plus mu square. If I add it n such times, it becomes n times sigma square plus mu square minus n upon n minus 1 times expected value of x square is sigma square by n. This is sigma square by n plus mu square. So all we have done is we have made the substitutions. Okay, then moving forward, so I'm erasing this off. So I can write, therefore expected value of s square is n upon n minus 1 into sigma square plus mu square minus n upon n minus 1 into, I can take n as the LCM, sigma square plus n mu square. Now guys, within these two terms, we can take n upon n minus 1 common. So sigma square plus mu square minus sigma square plus n mu square divided by n. Okay, erasing everything on the right hand side. So erasing all this, let's work it out forward. So this further becomes expected value of s square is n upon n minus 1 times, I can again take n as the LCM. So n sigma square plus n mu square minus sigma square minus n mu square. Now n mu square minus n mu square cancels. Okay, this becomes n upon n minus 1 into sigma square into n minus 1 by n. So n and n cancel, n minus 1 cancel. Therefore expected value of s square is equal to sigma square. Therefore s square, which is summation xi minus x bar square upon n minus 1, is an unbiased estimator of the population variance sigma square. So we have shown that s square is an unbiased estimator of sigma square. Now we can clearly show that the old s square is also biased. So let's show that. So I'm erasing the question now. Now we need to show what? We need to show that expected value of the unadjusted s square is not equal to sigma square, where all of us know what is unadjusted s square. Unadjusted s square is summation xi minus x bar ka square divided by n. So we can do the proof and we can show that it's a biased estimator. So my unadjusted s square is summation xi minus x bar square upon n, which I can write as summation a square plus b square. Again, we use this identity as I goes on from 1 to n, whole divided by n. So I can write 1 upon n times summation as I goes on from 1 to n xi square. X bar square, if we add it n times, we get nx bar square minus 2x bar into summation as I goes on from 1 to n xi. Okay, so this becomes summation as I goes on from 1 to n xi square plus nx bar square minus 2x bar into, we just saw a few minutes back that summation xi is nothing but nx bar. So my unadjusted s square is 1 upon n times summation as I goes on from 1 to n xi square minus nx bar square. So now if I take the expectations, I'm further solving it on the right hand side. Expected value of unadjusted s square is 1 upon n times summation as I goes on from 1 to n expected value of xi square minus n times expected value of x bar ka square. Okay, and from the previous proof, we know that expected value of xi square is how much? Sigma square plus mu square, and expected value of x bar square is sigma square by n plus mu square. So if I make the substitution, expected value of unadjusted s square is 1 upon n times, this comes out, so expected value of xi square is sigma square plus mu square. If I add it n times, it's n times sigma square plus mu square minus n times expected value of x bar ka square is how much? It is sigma square by n plus mu square. Okay, so if I open up the brackets, I get sigma square plus mu square minus sigma square by n minus, so if we further solve it, or I can first open up the brackets inside and then we can proceed further. So this is 1 upon n times n sigma square plus n mu square minus sigma square minus n mu square. So n mu square minus n mu square cancels, so this becomes n, or this becomes sigma square into n minus 1 by n, and you can see clearly it's not equal to sigma square. So we have shown that the unadjusted s square is a biased estimator of sigma square. Why? Because we have shown that expected value of unadjusted s square is not equal to sigma square. So I hope students have understood this proof as well. So I am erasing the initial part and then we can find the bias. What is the degree of bias? Okay, so let's work on finding the degree of bias, erasing all this on the left hand side. So therefore unadjusted s square is a biased estimator of sigma square, since expected value of unadjusted s square is n minus 1 by n times sigma square, which is not equal to sigma square. And if I want to find the bias, bias is nothing but expected value of unadjusted S square minus sigma square, which is expected value of unadjusted S square is sigma square into n minus 1 by n minus sigma square. So this is n sigma square minus n sigma square by n. We get the bias as minus sigma square by n. This is the bias. So I hope all students have understood. This is a very important question from exam point of view also. Okay, so I hope students have taken this seriously and have understood the proof behind this. Okay. And now there was one more question left. So let's do that question as well. So let me write that practice question for you. This is the second question for the day. Suppose the random variable x has a uniform distribution. Suppose the random variable x has a uniform distribution on 0 to theta. Show that theta 1 hat, which is max of x1, x2 dot 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 xn, is a biased estimator of theta. Okay. Also show that theta 2 hat, which is n plus 1 by n times max of x1, x2, xn, is an unbiased estimator of theta. Okay, so let's work this out. I request students to read this question once again. We are given that the random variable x has a uniform distribution on 0 to theta. We need to show that theta 1 hat, which is max of x1 to xn, is a biased estimator of theta. And we also need to show that theta 2 hat, which is n plus 1 by n times max of x1 to xn, is an unbiased estimator of theta. So let's first consider theta 1 hat. So consider theta 1 hat, which is max of the sample values x1, x2 to xn. Okay, so what do we need to show? We need to show that expected value of theta 1 hat is not equal to theta. That is, theta 1 hat is a biased estimator of theta. Now guys, we'll be proving this using theoretical argument. So we'll be using some logic. So first of all students should see this, that my x has a uniform distribution on 0 to theta, and my estimator is theta 1 hat, which is max of x1 to xn. Now when we talk about unbiasedness, so let's look at the proof. Now unbiasedness implies that some samples will yield estimates. Some samples will yield estimates that exceed theta, and the other samples will yield estimates smaller than theta. Okay, so if we want expected value of theta 1 hat to be equal to theta, it means some samples should give you estimates that exceed theta, and some samples should give you estimates which are smaller than theta. Only then theta will be the center. Okay, only then only then theta would be the center of theta 1 hat's distribution. When we talk about expected value, guys, what does this mean? It means some sample should give you estimates which are more than the expected value, which is in this case theta, and some samples should give you estimates which are smaller than the expected value, which is theta. But now I want to ask you one thing. Our estimator is theta 1 hat, which is max of x1 to xn. Now I want to ask you, will it ever overestimate theta? Answer is no. Can theta 1 hat overestimate theta? This is our question. Can theta 1 hat overestimate theta? Answer is no. Because theta 1 hat is the maximum of the sample value, and the maximum of the sample value cannot exceed the maximum of the population value. Why? The sample lies within the population. If the sample lies within the population, sample value cannot exceed the population value. So answer is no. Our proposed estimator will never overestimate theta, because the largest sample value cannot exceed the largest population value. Okay, so what do we learn? We learn that theta 1 hat will either underestimate theta, or it will be equal to theta, for a particular sample. Now since theta 1, now understand this, that for theta to be the center, theta 1 hat should underestimate theta some of the times, and theta 1 hat should also overestimate theta some of the times. Only then theta will be the center or the expected value. But we have seen in the proof logically that theta 1 hat will never overestimate theta. It will either underestimate theta. Why underestimate? Because the sample value can be less than the population value, or the sample value can be equal to the population value. But the sample value cannot exceed the population value because the sample comes from the population. So if we go by this logical argument, what do we understand? We understand that therefore theta 1 hat is a biased estimator of theta. Theta 1 hat, which is max of x1 to xn, is a biased estimator of theta. I hope students have understood this proof. We have used logic here. We have not used any math. So I am repeating it once again. We were given theta 1 hat as maximum of the sample values. We need to show that it's a biased estimator of theta. And x has a uniform distribution on 0 to theta. Now, I am again revising it. For an estimator to be unbiased, it should underpredict the population parameters some of the times, and it should overpredict the population parameters some of the times. Only then the population parameter will fall in the center. That means in our solution, theta 1 hat should overpredict theta some of the times in some of the samples, and theta 1 hat should underpredict theta in some of the samples. But we have pointed out logically that our estimator theta 1 hat cannot overestimate theta. Why? Because if you take any sample value, any particular sample value can never exceed the population value. In other words, maximum of the sample value cannot exceed the maximum of the population value, because the sample is coming from the population itself. So we have ruled out the possibility that theta 1 hat can overestimate theta. That means all we are left with is two possibilities. Either theta 1 hat can underestimate theta, which is perfectly possible because the sample value can be, the maximum of the sample value can be less than the maximum of the population value, or theta 1 hat can be equal to theta for any one particular sample. But theta 1 hat under no circumstance for this question will overestimate theta. And since that is not possible, theta cannot be the center of the distribution. That means theta 1 hat is a biased estimator, because expected value of theta 1 hat for this question will not be equal to theta. So hoping that the students have understood this question, okay, and have no doubts. Now, suppose in the question, if I add one more thing, so I'm erasing all this now. Now we are going to prove the second part. The second part of the question was that we need to show that theta 2 hat is an unbiased estimator. So first of all, I am erasing this logical argument which we have done. Let me erase this argument. Okay. So suppose in the question we were given the value of theta 1 hat. Suppose we are given that expected value of theta 1 hat is equal to n upon n plus 1 times theta. You can clearly see that this is not equal to theta. Hence, theta 1 hat is a biased estimator. Now, suppose this value is given to us. Now, what do we need to show? We need to show that theta 2 hat is an unbiased estimator of theta. We need to show that theta 2 hat is an unbiased estimator of theta. So guys, if I look at the proof, expected value of theta 2 hat will be expected value of, what is theta 2 hat? N plus 1 by n times max of x1, x2 dot 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 xn, which is n plus 1 by n is a constant into expected value of max of x1 to xn. Now guys, max of x1 to xn was what? Theta 1 hat. Max of x1 to xn is nothing but theta 1 hat only. Okay, and we just showed that expected value of theta 1 hat is, it was given to us in the question, n upon n plus 1 times theta. So you can see n and n cancel, n plus 1 cancel. So what do we get? Expected value of theta 2 hat is equal to theta. Therefore, theta 2 hat is an unbiased estimator of theta. Now, in order to prove this in the exam, you will be given this part. You will be given that mathematically expected value of theta 1 hat is equal to n upon n plus 1 times theta. Okay, this information will be given to you in the exam. Okay, you using this information, you will show that theta 2 hat is an unbiased estimator of theta. So we got expected value of theta 2 hat as theta. So we have shown that theta 2 hat is an unbiased estimator of theta. So hoping all students have understood this question as well. So we had to show two things. First, using logical argument, we have shown that theta 1 hat is a biased estimator of theta. And then using this information, we have shown that theta 2 hat is an unbiased estimator of theta. So hoping all students have understood this. And then we do the third property for the day. So our practice questions are over. We now do the third property. So definition, this is the third property called efficient estimators. The first property was linear estimator. The second property was unbiased estimator. Today we are doing efficient estimators. So let theta 1 hat and theta 2 hat be two unbiased estimators of theta. Suppose theta 1 hat and theta 2 hat are two unbiased estimators of theta. Then theta 1 hat is said to be more efficient than theta 2 hat if and only if variance of theta 1 hat is less than variance of theta 2 hat. So if we talk about two estimators, theta 1 hat and theta 2 hat, okay, then theta 1 hat will be called a more efficient estimator than theta 2 hat if the variance of theta 1 hat is less than variance of theta 2 hat. So I hope students have understood the condition. That estimator which has a lower variance will be more efficient. Okay, so let's look at a practice question on this. So let's look at a practice question. So consider two estimators, theta 1 hat and theta 2 hat of the population parameter mu, defined as theta 1 hat is equal to x1 plus x2 plus x3 by 3 and theta 2 hat is 2x1 plus x2 plus x3 by 4. Now the question asks us, show that theta 1 hat is more efficient than theta 2 hat. So let's see how we show this. So let's first find variance of theta 1 hat. Variance of theta 1 hat will be variance of x1 plus x2 plus x3 by 3. Okay, this is what our variance comes out. And if you further work it out, this is 1 upon 9 times variance of x1 plus variance of x2 plus variance of x3, which is 1 upon 9 times, all of them have the same variance, they are independent and identically distributed. So it comes out as sigma square by 3. And if I do variance of theta 2 hat, it is going to be this. Which is 1 upon 16 times variance of this, which is 1 upon 16 times 4 times variance of x1 plus variance of x2 plus variance of x3, which is 6 sigma square by 16. And 6 sigma square by 16 I can write as 3 by 8 times sigma square. So what do we observe? We have found the variance of theta 1 hat, it has come out as sigma square by 3. Variance of theta 2 hat has come out as 3 by 8 times sigma square. Clearly, variance of theta 1 hat is less than variance of theta 2 hat. All of us know 1 by 3 is 0.33, but if I do 3 by 8, it turns out as 0.375. That means variance of theta 1 hat is less than variance of theta 2 hat. Therefore, theta 1 hat is more efficient than theta 2 hat. So if I look at the variances, we have seen that variance of theta 1 hat is less than variance of theta 2 hat. So theta 1 hat is a more efficient estimator than theta 2 hat. Okay, so this is where I stop in the lecture today. I hope all students have enjoyed the lecture. Any doubt, you can unmute your mics and ask, or call up or mail me your doubts at divineschoolofeconomics@gmail.com. In the next lecture, we will continue with the further properties of point estimators. So this is where I stop.